Chinmay and Tanmay. Who here know Chinmay and Tanmay already?
I know them, just cannot tell which one is which.
Okay. Okay.
They have
I mean, you could swap that. We probably couldn't tell. Their brand is the Tinker Twins, right? So they're PhD candidates from Clemson University, and I'll let them also introduce themselves, their lab, maybe Venkat.
So, good afternoon everyone. We will be delivering a small talk around digital twins, developing and using them for autonomy verification and validation. We are from Clemson University's International Center for Automotive Research, the Automotive Engineering Department. A little bit background about ourselves if someone is not satisfied with the introduction that Dr. Garcia just gave, is basically we did our undergrad from India in mechatronics engineering, where Chinmay got the gold medal and I got the silver. And then we directly transitioned to the US at CU-ICAR for PhD. And that's where we are working at the ARMLab, which stands for Automation, Robotics and Mechatronics Lab, which is directed by Dr. Venkat Krovi. Both of us started our research from robotics and autonomous systems in our undergrad, and now coming here we are specializing in autonomy-oriented digital twins, where my focus area is on modeling, estimation and simulations to create digital twins for both the vehicles and their environments. And Chinmay is targeting the other end of the coin, which is using smart techniques for augmenting, adapting or identifying the sim to real gap and then bridging it using scientific machine learning methods as well as formal methods. And we will of course make clear of what the pictures here look when we go through the slides. So what we are going to talk about today most prominently is something called Autodrive ecosystem, which we have developed, and it developed as a research internship project at Nanyang Technological University, Singapore. We continued at it at our undergrad as a bachelor's thesis, and coming here we are again keeping it alive through our PhD. And this is kind of the high level agenda. We will be introducing the ecosystem first. We'll talk about some of the research projects that it has enabled us to do. We'll also talk about an interesting aspect of competitions, and finally we'll give a short hands-on tutorial or just a demo for everyone. So let me start by introducing what Autodrive is. On a high level, it looks something like this, where you have the left part, which is the Autodrive testbed and simulator. The testbed is the physical system, and the simulator is its corresponding digital replica, where you've got different vehicles and different environments or infrastructure, and then there is like granularity within those. So the pictures on the left, the top, you have different vehicles. The first and the second column in there is the real world photographs, and the second and the fourth are the corresponding digital twin photographs captured from Autodrive simulator. And you can like already start seeing the graphical realism, but there is dynamics fidelity as well. And then we have the environments across different scales and operational design domains for the different vehicles. Of course, you can also put the full-scale off-road vehicle in the small, say the tiny town environment that you have there, but that will be something fun to do. But you have more representative scenarios for off-road driving, you've got on-road driving, you've got small-scale robots, indoor environments, and all of those that fit the scale and use of the different vehicles that you see in the top left. And on the right side in the picture here, you have what we call the Autodrive Dev Kit, which is a set of programming APIs, tools, frameworks to develop, debug and deploy autonomy algorithms. And these can be for the autonomous driving tasks as well as smart city management. And we have like listed a few APIs here, which also include the ROS and AutoWare stacks. And on the right, you also have different human-machine interfaces. So this is not only for autonomous driving, you can also immerse humans or human drivers in the loop for teleoperation, for collecting data sets and whatnot. And you have different degrees of immersiveness for both observing the digital twins and interacting with them in the virtual world. So a quick look at the different vehicles. So as I highlighted earlier, this is a representative graphic which shows the physical and digital twins of different vehicles. On the top you have a small scale, and the scale increases as you go down, and from left to right you have got different operational design domains. So Nigel, which is the native vehicle of Autodrive, typically targets indoor lab settings, on-road driving conditions, F110th, most of you would be aware of what F110th is, or now called RoboRacer. It's basically a platform for, again, indoor, or you can also go outdoors with it, autonomous racing. Then you've got mid-scale robots like the Husky or Hunter, which can do both indoor and outdoor deployments on road as well as off-road. And then you have got full-scale vehicles as well, like the OpenCAV, which we have at ICAR, for full-scale autonomous driving, typically on-road or in-campus driving, and the Razor, which is typically for off-road autonomy. And here is just a quick glimpse of all of the different digital twins in action. So as I said, you have different representative scenarios for each of the different vehicles. You can of course use the Razor in that kind of environment, or use the F110 in off-road to just see what it does. But of course the real aspect here is that you don't just have the digital replicas of the vehicles, but also the kinds of environments that you wish to deploy the autonomy algorithms in. And so, going a little bit in depth with the different environments, you've got, as I said, different scales and complexities and operational design domains that they target. You've got simpler environments for in-lab setups, typically constructed from vinyl stickers or cardboard boxes, or the air ducts in case of F110 racetracks. You've got mid-scale environments which can be indoors or synthetic, like the proving ground you have with traffic cones, or you can have more realistic and diverse feature-rich environments for mid-scale robots which can be deployed in the field as well. And in full scale, you typically have on-road and off-road settings where you can target both downtown-like environments or generic rugged off-road environments. And one thing that we have tried to do is have a benchmark scenario that we call the tiny town across all the different scales, just to benchmark your algorithms as they scale from small scale to mid-scale to full-scale deployments. So here is just another view of constructing the environments. So in AutoDrive, we have given a lot of flexibility on how you can develop your environments. You can have 3D artists create them from scratch. You can use procedural generation, or you can use data-driven 3D scene reconstruction to actually have digital twins of real-world environments. So here we have, for example, what you see is a data-driven reconstruction of an off-road area that we used just a 3D LiDAR from an actual robot to collect the data, and then reconstructed its geometry in sub-millimeter level accuracy. But what you can also do here is infuse camera data, and that way what you see here is not a photo taken from a camera, but an actual reconstructed 3D scene from our campus. And what it allows you is benchmarking it in terms of its geometric accuracy. As you can see, the point cloud overlaid, that was the real world point cloud, by the way, not the one from the simulation. And then more detailed collision mesh, for example, that now enables you to interact with the environment in the virtual world. And of course, you can already start seeing the photorealistic or graphical quality. And what you can do is basically start adding assets to it. And again, you can choose either data-driven assets, like for example, we have this car over here, or the traffic sign. These were actually reconstructed from real-world data. Or you can have synthetic 3D models, like for example, the pedestrian that's there, which is actually a model that was generated from a photograph of a person. The person is Chinmay. And you have also other 3D models like the road barrier or a cement rubble pile. And what you can do is now infuse physics with these assets. So even with the data-driven assets, so you can now have rigid body collisions, add vehicle dynamics properties, or any other fancy stuff that you want to do with it. And here, for example, we are showing that it has basic rigid body properties. You can just lift them up and the gravity will take care of making them fall down on the ground. And also add collision properties to it to detect the momentum transfer or the mesh-mesh interference. But what's more interesting is now you can actually start deploying your vehicles in the virtual world, which is now reconstructed. And that's the OpenCAV digital twin that we have running in the digital simulation from the ICAR campus. And here what you can see is it is not just photorealistic in terms of the camera field of views, as well as the perception in general, the kind of images that you would expect from the full-scale vehicle on campus, but it also has the geometrical accuracy to make sure that your LiDAR point cloud or even radar information or any other sensors are also perceiving the environment as naturalistically as possible. And most importantly, doing all of this in real time at 30 Hz frame rate. So that's one aspect of it. Another aspect is having a static scene is okay, but you kind of want to introduce variability in your simulations to make sure that your algorithms are working fine across different parametric conditions. And so here, for example, we have a video showing the adjusting of time of the day as well as different weather conditions. So in the top two rows, we have the scene going from dawn to dusk to night. And in the bottom two rows, we have clear, cloudy, foggy, rainy conditions and snowing in the last couple of videos. And all of these weather effects and the time progressions can be generated procedurally, so you can automate it, you can parameterize it finely. You can also choose from preset times or weather conditions, but everything is as flexible as you hope it should. And then what you can also start doing is using generative AI or agentic AI, as people have started using these days, to introduce more and more naturalistic variability in the scene. So for example, here we have a prompt that says add a jaywalking pedestrian across the ego vehicle's path. And here the model basically searches for the ego vehicle's path that the vehicle is trying to progress along. It then, one thing that's interesting is if you see the video, it actually added a pedestrian sign even when we didn't ask it explicitly. So that's kind of context aware learning, where you can see some interesting kind of scenario variations even without expecting them, and that's something that adds naturalistic variations rather than parametrically sweeping across different sets of possibilities. And that's what we think would create a more unified framework for scenario generation rather than relying solely on script-based languages or scenario description languages. And what you saw can not only be done on local compute, but you can actually deploy everything in the cloud in high performance compute clusters. So what we see here are different modalities of simulation parallelization. So you can have instance parallelization, of course, where you run multiple instances of simulation. But what's more interesting is you can now just parallelize different environments within the same simulation instance. So that's what you see in the top left, where we have replicas of, say, 25 different environments training the RL agents parallelly to navigate a multi-lane intersection. And what you see in the bottom right is parallel agents within the same environment. So this is the F110 race cars. You have the same environment, that's the racetrack, and you have multiple families of two agents. So there's one red agent and one blue agent that are racing against each other, but you're now replicating these multi-agent families and making sure that they don't collide with the parallelized instances. So for example, in the camera field of view here, for one of the agents, you can see that it's not perceiving any other cars that are driving in there. It's only perceiving its two opponents, and same goes with the LiDARs or the collision checks as well. And what we see here now is the cloud-based deployments. So we have different configurations again. We got a chance, we were fortunate enough to experiment these with different types of clusters. So here is a sample framework for Kubernetes-based deployment in a private cluster, where you are typically allocated, or you know the kinds of resources that are available to you, and you can time slice the GPUs accordingly and then deploy your simulation instances and autonomy algorithms as such. And that's what the deployment looks like, where you have a web viewer client, which is basically taking all the simulation streams from the server and visualizing it on a thin client, so that a human operator, for example, could manually assess the simulations as they are running in the cloud to make sure that everything is going as expected. And you can have a similar layout for data analysis as well. But what you have here is another cluster configuration which we have at Clemson, which is the Palmetto cluster, which is a publicly shared resource across the entire university. And this is where things start getting interesting, because you no longer have deterministic access to resources. You have to play with the job schedulers to make sure that you are waiting until the resources are freed up, and you basically spin up your simulations accordingly. And that's what this kind of framework does. It also has interoperability in terms of the kind of architecture that the cluster is having, as well as pooling containers or your source code from the container registry or the repositories upstream. So in terms of user experience, that kind of adds a little bit flexibility in terms of how you deploy your workflows. And this is what it looks like. So again, the same web viewer now, since this is a much powerful cluster, we could parallelize even more simulations in the cloud. And what you see is again different times of the day and weather conditions being simulated to validate the autonomy algorithm. And what you see in the bottom are the two different cluster architectures where we have two different schedulers, namely the PBS and Slurm managers, as well as different hardware resources in the cluster as well. Coming to the different APIs and HMIs, as I highlighted, AutoDrive offers a range of APIs and HMIs to interface with the simulations. So, for example, you have basic programming languages like C, C++, or Python, as well as MATLAB and Simulink, or you can leverage the existing frameworks such as ROS, ROS2, or AutoWare to develop your autonomy algorithms and interface them in real time with the simulator. Or what you can also do is use different HMIs, the human-machine interfaces, to observe and interact with the digital twins, as you see in the video on the left, where, for example, right now I am controlling the razor in the simulation using a keyboard, but you can do the same pretty much with a joystick, a mouse, a driving rig if you have one, and if you're lucky enough, a motion rig to now experience the kind of jerks and accelerations that the physical vehicle would give you, but only in the safe environment of your lab. And then finally you can do an XR immersion to just get immersed totally within the virtual scene. And if you couple this with the motion rig that I showed earlier, it's really fun. So we have also used AutoDrive ecosystem to collect a lot of data sets. These are for both physical as well as virtual vehicles across the different scales and operational design domains. We have used the data sets primarily to, first of all, validate the simulations, the digital twins themselves, as well as deploy and formulate and deploy data-driven learning and control algorithms for different research projects. So I'll now ask Chinmay to take over the presentation and highlight some of the research projects as well as other aspects of the AutoDrive ecosystem. Thanks, Tanmay. So I'll just go over some of the relevant research projects that we were able to accomplish with the framework. So the first project that we were able to do was common autonomy validation framework across the different scales and operational design domains. So the idea was just very simple here. We wanted to stress test the algorithms, and in this case we are using the AutoWare stack. The problems determined were based on the operational design domains of the different vehicles. So we have autonomous parking, for example, we had goal-to-goal navigation. And the idea was to now see what are the different levels of fidelities that we can play around with. Does the scale matter? If so, how much? And all those kinds of studies wherein we also want to see if having a 2D map of the environment is sufficient enough, or do we really need to have a 3D map of the environment. So in some of the examples that you will see, for the first is it was very simple. With a very small scale vehicle, you could get away with a 2D map, such as this or the earlier case. But the challenge comes as you scale up, because there the vehicle dynamics as well as the vehicle environment interaction becomes more complicated. That also adds to the latency of if your simulation as well as the driving stack is running on the same computer. One thing that is worth highlighting here is with AutoDrive, we have, if you look at the GUI on the top left, we have a configured label setup where the simulator and the ADS could run on the same machine, or they could be on different machines. Just as long as they are connected via same common network, it should work seamlessly. So in this example, what you see is a very simplistic on-road driving condition and then an off-road deployment of the very same algorithm. But of course, as expected, we can get away with a 2D map in such a simplistic environment where we can actually project the entire environment as a 2D figure, for example. But it gets more complicated because the terrain gradients and elevations are much difficult to anticipate with just a 2D representation. Of course, you can do that, but then we have found that in sim-to-real deployments, you need the algorithm, like for example, the controller gains or scheduling needs to be modified for it to work with higher terrain gradients or elevations. So you need a better, like a high fidelity representation of the environment. Even in this case, for example, one thing that is worth mentioning here is for the small scale vehicles, especially, and even for the mid scale vehicles, we were able to do a zero-shot sim-to-real transfer of the algorithms without modifying any perception algorithm parameters or the control algorithm parameters, which are the two main interfaces where we experience the sim-to-real gap. The planning stage is still reliant on the perceived data, and generates the control commands, but that still lives within the virtual space. The perception and the control interfaces are where we encounter the simple gap. And so after that, what we experimented with and were able to successfully achieve is, as Tanmay highlighted in one of the earlier slides, a deployment of autonomy validation framework in the cloud. So here we are leveraging the Polaris Razor digital twin, and the environment is naturally an off-road environment, but we are introducing variability in terms of the times of the day and weather conditions. This is the cluster specification. As Tanmay highlighted, this was a sandbox cluster, which was a very private resource that we had access to. Throughout the time, it was not shared, so we knew that we had all the nodes at our disposal. Just one thing worth highlighting on this slide is that we are just using the third node on the compute cluster, because the first two nodes were scheduled for some other jobs, but we had dedicated access to the third node as highlighted. And we had time sliced the GPU according to the frame rate requirements of the simulator. So we were just to ensure that we are making the maximum out of the compute availability. And as Tanmay highlighted in one of the earlier slides, this is what the deployment looked like. But what is valuable here is, once the deployment is done, we get access to all the data that was generated out of that deployment, and we can easily do a high-level pass-fail analysis of this. So for example, in this case, the candidate autonomy algorithm that we were testing was pretty simple. It was just a candidate wherein the Razor, autonomous Razor, is driving along a dirt trail, and it encounters a herd of animals down the path, which is not expected, but certainly possible in off-road conditions. And then what it has to do is analyze if the objects in front of it are of certain class, meaning is it safe to just run over them, or is it unsafe to or unethical to basically collide. So if it's something like a small rock or something that the vehicle can easily handle, it can basically run over that. But if it's something like animal or a big log of a tree or something like that, then it needs to stop. So that was the high-level algorithm that we had implemented. Of course, there are granular details to it, basically giving it an automotive scale reliability context. For example, if there is a nighttime condition, do you have automatic trigger of the vehicle lighting system and things like that, which aid in the perception. But the high-level pass-fail analysis, for example, we just took 4 different YOLO variants just right out of the shelf. We didn't retrain them on any kind of data that we're supposed to encounter. These are pre-trained models on the COCO dataset. And we just made a simple analysis as to how many test cases have passed versus how many have failed. And there were 128 total test cases to run here. And we can see all the data that was generated out of this. One thing maybe I can just quickly highlight out of all the data that we have here is the distance to collision, or DTC metric, wherein we had a factor of safety of a few meters. So the vehicle is supposed to stop a few meters ahead of the animal herd. And we can see that in many cases where we have model variants such as YOLO V3 or V2, the factor of safety was maintained, but in certain cases, like the tiny models, which are more performant models but at the cost of the detection confidence, what you observe is the models start dropping below the factor of safety or even collide in certain cases. So this is the kind of analysis where we can basically look at the detection confidence or the detection size or the consistency to find vulnerabilities in the perception part of the algorithm. Then we can look at things like the timing of AEB triggers or autonomous emergency braking triggers, or the distance to collision metrics, or the collision count that was resulted out of the simulation, to get a sense of how well the planning stage of the algorithm is working. And then we can look at the timing and trigger of the throttle and brake commands for the vehicle to get a sense of if the control part of the algorithm or the pipeline is working correctly. And then going a stage beyond that's just validation of the autonomy algorithm itself. What we also wanted to do is a stress test of the cluster itself in terms of how well we can handle or allocate the simulation instance parallelization. So one thing that's again worth highlighting is that all of these test cases that I mentioned were run parallelly and not one after the other. So as to make sure that we are making the most out of the HPC resources that we have. Of course, they can be sequentially executed, but then it adds to the time that you need for generating the test results. So this is a result of, so let me just introduce what the plot here means first of all. So we have at the beginning 16 simulation instances that are running parallelly, and then we drop a workload after a few time steps consistently to see how the cluster performance is affected by the simulation parallelization workloads. So we can see that the memory drop is pretty linear. Of course, it's not perfectly linear, but it's pretty close to linear profile. In CPU usage, we can see that it's a constant trend till a lot of simulation instances need to be dropped for it to considerably drop below 50% of usage. And in terms of GPU power and GPU usage, what we can observe is a very interesting trend, which again, as I have mentioned, if you have, let's say, so this is 16, so somewhere around 4 or 5 simulation instances, it doesn't really matter, because as I mentioned, the GPU has been time sliced. It doesn't really matter if you are running 16 versus 5 different simulation instances. The resource utilization is going to be pretty much the same. Same applies to the power. So when you are parallelizing, you're not just saving on the time, you're also saving on the compute usage as well as the power usage that you are essentially expending at the cost of this testing analysis. Finally, one step ahead was to, now that we have this framework ready and set up, we wanted to apply a more methodical approach to definition of the autonomy algorithm itself in terms of its variants or the test parameters, and then making sure that we are using something like model-based systems engineering framework to tie in the system requirements and have a critical analysis of the algorithm. So that is where what we have done is exactly the same scenario that I explained earlier, but instead of just deploying the simulations and generating the data out of it and then manually processing and analyzing it, what we have is a concurrent model-based systems engineering framework wherein you can define each component of the subsystem that you have under test. You can define the different variants that it has, and then you can automate and execute all of these simulations parallelly. So here we have leveraged MathWorks System Composer, which allows us to do this. We can parametrically define the test parameters as well as the algorithmic variants, and then we can execute them one after the other. And we also have a short demo that we would give at the end of the presentation to just understand or feel how it looks like, the entire validation process. And again, here we are running the same 128 test cases that we ran in the cloud.
Are all of these test cases manually specified?
Typically, yes. So manually specified in the sense you don't need to specify each and every test case. You can have a parametric sweep across a set of parameters. So for example, here we only define the different times of the day and the weather conditions, and also define the different algorithmic variants. So here, for example, we have 6 different perception models, 2 different planning models, and 2 different control models that are being validated simultaneously.
So you're creating different use cases for the different ODDs?
The ODD is still the same in this case, but yes, that is also a possibility.
Okay, because I know that's what they do for like the AutoWare evaluator.
Right.
So I'm wondering if this is a similar. It's basically done similarly here. It kind of sounds like it might be, but I'm not sure.
I'm not entirely sure about how AutoWare evaluator works, to be honest. But the idea here is to just the test specifier only needs to define what are the test requirements, what are the different test parameters that need to be swept across, and then if there are, what are the different algorithmic variants you have. And based on the 3 definitions, it basically generates the test harness and executes all the tests and generates the report automatically.
Yeah, because like the ODD working group keeps track of for AutoWare keeps track of the different use cases of the ODD, and they have, like, for example, slides specifying start and end positions of the autonomous vehicle, traffic participants, locations, trajectories, the map structure for this particular test or a particular map, and I'm wondering to what extent that's basically, it sounds similar.
Similar, yes.
Okay.
So the idea, at least in this case, because I know the framework inside out, is that you would define all of those as test parameters, and then you could sweep across all of them automatically. And just as a number, we were able to generate a detailed report of about more than 2,000 pages for 128 test cases. Of course, all of that information is at our disposal. Using it or not is an option. And then here is another work that is pretty interesting. But what we are doing here is, as Tanmay highlighted, leveraging simulation parallelization to efficiently train reinforcement learning policies. But instead of just remaining in the simulation, because doing everything in simulation is cool, but for any of these kind of systems to be valuable or useful to humans, we need them to be deployed in the real world. So from here on, I'll just give a few examples of how this framework is basically helpful in terms of devising the sim to real aspect as well. So here we had just two simple case studies of training multi-agent reinforcement learning policies for cooperative as well as competitive scenarios, and then transitioning them from virtual world to the real world, but with a fascinating twist, as you will see in the upcoming slide. So here, this is the formulation where the problem is, as Tanmay highlighted, a multi-lane intersection traversal. So the ego agent, that is this agent, needs to traverse to the other side of the intersection, and all the other participants are stochastically varied in their behavior. So they might cut in, and it's an uncontrolled intersection, so you don't have any stop sign or any regulatory barriers like traffic lights or anything. It is a very stochastic scenario. So we just trained the policies by parallelizing the environments in this case to demonstrate that aspect, because the problem is related to the environments. But what you could also do is, as I'll highlight in one of the upcoming slides, is agent parallelization for different case study. And again, here we had a single agent learning scenario wherein just the ego vehicle is learning, all the other participants are just controlled by a simple heuristic. And then we had a multi-agent learning scenario where all of these agents are learning concurrently to traverse the intersection without colliding or violating any traffic rules. And then in the sim-to-real deployment, what we can leverage is the best of the both worlds. So you have the ego vehicle in the real world. You don't need the environment. You don't need the peer vehicles. And what you can do is essentially immerse the real vehicle in the loop with the simulator. So this vehicle update is based on the state estimate updates of the real vehicle. And basically once this vehicle has received the data, we know that the real world and the virtual world are in sync. And then we can start the simulation for all the other vehicles and the environment in the virtual space. We don't need that in the real world. And the vehicles will still interact in the virtual space. And this vehicle will basically decide what, based on the policy that's been trained, what commands to execute, and those commands will be relayed back to the physical vehicle to execute them in the real world. So that basically completes the loop, wherein you can have a sim-to-real deployment without necessarily having the need to have all the resources of different vehicles or different environments to be set up in the test environment. And then we tried the same with F110 as well, wherein, as you might be aware, the problem statement is pretty simple. We are having two different agents that are racing against each other. So that's the behavior. And one more thing that we wanted to just try out in this case study was, instead of just doing pure reinforcement learning, can we guide this reinforcement learning with some human demonstrations? So this is a demonstration guided reinforcement learning problem that we are trying to solve, when we have already given a few demonstrations to the agents of how to drive around the racetrack, but they need to reinforce the habit of or the behavior of racing along the track. So we have a different reward system. I'll not go into the detail of it in the interest of time. But again, the idea is same. You have the policies trained in simulation by parallelizing the agents in this case, because the environment is common across the deployment. So we don't need to vary the environment. But again, one idea is to, while we are parallelizing these different environments or agents, an idea is to imbibe domain randomization in terms of, for example, affecting when we are parallelizing environments. Each parallelized instance of the environment could have a different friction coefficient or other environmental properties. Same applies to the agents as well. So each of these parallelized vehicle could have a different suspension property, could have a different tire property, could have a different mass, or anything, to be honest. And that will basically create a generalized policy that is easier to deploy from simulation to reality. So this is just testing in the simulation where we observe some cool behaviors. So in the first, we see a block overtake sequence wherein the red vehicle keeps blocking the blue vehicle, and then at the end the blue vehicle is basically just cutting in across the red vehicle to take the lead. And on the right hand side, this behavior is basically let pass and overtake, which was even something that we didn't really anticipate would happen, is that the red vehicle essentially lets the blue vehicle take the lead, but then what it does is cuts in between the track bound and the blue vehicle to take the lead again. And then again, a similar framework for deployment wherein we don't need the racetrack in the real world, we don't need another vehicle, although we had a bunch of them lying in the lab. So this problem is pretty much a scalable framework wherein you can deploy really high number of agents in the real world without necessarily having all of them physically present. You can have the digital twins of them immersed in the loop with the real vehicles or the environments. And then this is another work where we have a larger scale vehicle operating in an off-road environment. Again, as I mentioned, accounting for the terrain gradients is one of the critical aspects here. So what we have is we create a digital twin of the environment itself. We compute the terrain properties and the terrain gradients offline, and then we use them in an online fashion as demonstrated in this framework to create a model of the vehicle first of all, as well as create optimal mission plans for navigating from one point in the environment to the other. And then using the data-driven model that we have, we can have a data-driven motion planning and control framework and utilize the terrain information in this based on the vehicle localization information and use that to guide the sim-to-real transfer. So that is the kind of work that we have recently accomplished, and this has been accepted at ICAR for publication. So as we'll see in the stage 3, which is validation of the framework, we have the deployment in AutoDrive Simulator, and we can see the resemblance in the real world deployment as well. We have validated across a bunch of trajectories, which is basically, first of all, we have different heuristics for the global mission planning based on the terrain information we have, which account for things like safety, like what are the terrain gradients you should avoid in order to prevent a rollover or things like that. You have energy efficiency, where you try to avoid the elevation changes. And what we observed in between simulation and reality, wherein the augmented approach is the one that has this digital twin information, whereas the non-augmented approach does not have the digital twin information in the mission execution. And what we observed is for optimized trajectories that are generated out of the terrain-informed mission planner, we don't see a huge difference in the trajectory tracking performance. But when we start to see the pattern, we can see that in case of the non-augmented approach, it's pretty sluggish in terms of its behavior. Whereas when we have the terrain information imbibed from the digital twin, it's much more efficient to track the trajectories in the simulation as well as real world. And so we stress tested with a more complicated trajectory that did not have any global considerations as to what are the terrain gradients that are that the trajectory is traversing, or what are the elevation changes. And we clearly see that the trajectory literally failed in simulation as well as the real world for the non-augmented approach, wherein we had to literally intervene because the vehicle was driving towards a tree. And in case where the digital twin information was at our disposal, we could leverage that to basically guide the agent to still track the trajectory efficiently. And even if you look at the mode of failure in simulation as well as the real world plots, you see a very close resemblance as to where or at which point the failure occurs, which is pretty valuable. And then going to full-scale testing, one thing that's fascinating is we can immerse the physical vehicle in the loop with environment digital twin or other vehicles. So we have the vehicle running on a dyno here, and we are updating the digital twin live, and the first person projection of the camera feed from the vehicle, egocentric camera view, is projected in front of the vehicle to make it believe as if it's driving in that scenario. So we have, as in case of the multi-agent reinforcement learning deployments, we have the access of real world vehicle dynamics coming in from the data that we have, and that's used to update the simulation in real time. And what we can do with this kind of a framework is basically a hierarchical flow of simulation, which is just vehicle dynamics modeling and virtual environment representations, going to emulation, where we can just bypass the sensor feed. Instead of projecting the sensor feed in front of the vehicle, we could just inject the ground truth, for example, of the different obstacles or objects in the scene. Or we could emulate the steering forces. Since the vehicle is running on the dyno, we can't really steer it. So one way is to just estimate the steering wheel by measuring the steering wheel angle, which we did from the CAN data. of the vehicle and then emulate the steering force using a steering force emulator that fits under the vehicle, wherein you can basically emulate the forces on the tie rods of the steering mechanism. And what that does is basically in the simulation you can still update the steering or the lateral vehicle dynamics, where you don't need to do that in the real world. And finally, coming to stimulation, we can physically stimulate the sensors as if they are perceiving the information, as you can see in the video. Or there is also a possibility in terms of the dynamics to control the individual roller velocity or road loading conditions to emulate the different scenarios that are possible. So you could basically emulate gradients and things like that. And then finally, as we demonstrated with the small scale vehicles for reinforcement learning policy deployments, we carried a similar kind of experiments. Of course, this is not reinforcement learning. We have just a simple study of autonomous emergency braking across manually driven vehicle with static first person view with dynamic immersion, like applying the VR headset to basically when the driver is rotating the head movement, the simulation feed view is updated. Then we have an autonomous vehicle and a connected autonomous vehicle. The difference wherein is whether it has the information from the environment or not. So does it know that there is another vehicle that's going to cut in front of it or not? Again, the scenario is simple. It's a jump scare scenario wherein a vehicle just cuts in across at the intersection. And just to ensure safety, what we can do here is, instead of having any vehicle that comes or cuts in front of the real vehicle, which could be a safety hazard, we just do that in the simulation and we use that information to relay to the autonomous driving software stack. And again, similarly, when the vehicle is driving in the real environment, which is our campus, we can update the state estimates to match or synchronize it with the digital environment that we have. So that basically covers the research aspect. And one more thing that we have recently started is to support competitions. So we had the first F110 Sim Racing League at IROS, wherein we had the digital twin of the F110 vehicle and the racetrack given to different participants, and they were supposed to train or build their algorithms for racing their vehicles autonomously in such an environment. So the competition itself consisted of two stages. One is the qualification round, wherein safety is the only consideration. Basically, we are assessing whether the participants are able to complete multiple laps without colliding. And in the competition round, which is the final race, they were asked to go as fast as possible and ranked on a leaderboard based on their timings. And again, there was a change in the track between the two phases, and the competition track, the final competition track, was just released a day before the competition, so as to check the robustness of the algorithms that the teams have been developing. The deployment looked something like this, wherein we have adopted a containerization approach similar to the HPC deployments I talked about. The containers of the dev kit as well as the simulator were provided to the competition participants, and what they had to do is basically fill in this void, which is the autonomous driving software or racing software in this case. And again, we gave a flexibility of using distributed computing or graphical rendering versus headless computing modes, where participants from different groups need not have the compute requirements for running the simulator as well as the dev kit all on the same machine with graphical rendering. So to just ease that pain point, but the actual competition deployment was done on the same workstation to make sure that the performance is analyzed on the same compute specifications. And after the competition, we had access to all of the data. So we can basically do benchmarking as well as analysis of all of this data. This data was also provided to the teams who participated, by the way. So they could analyze all of this data and determine where their algorithm is basically lacking. For example, is it cutting in the chicanes efficiently, or do they need to optimize their algorithms? If so, which parameters are being affected and what needs to be optimized could be inferred from such kind of data. What this also helped us as organizers is to basically set automation scripts wherein we could analyze which lap is the vehicle currently going in, has it met the qualification criteria, or does it need to be disqualified, and what are the general trends or other performance evaluations for the specific team that we are working with. Then we had a second deployment of the competition at CDC 2024, which is pretty much the same, except for the part where we again switched the competition track a few days ahead of the competition to make sure that the algorithms that the teams are developing are robust enough. And then other things remained pretty much the same, but just few changes in terms of we optimized the framework to be more real time, in the sense it could run real time even on lower grade computers. And we also ported the framework from Foxy to Humble based on the request of multiple teams, just so that it just stays alive, and it's basically the teams can leverage some of the newer packages that are available in ROS to Humble, which were not in Foxy distribution. Again, a similar analysis was done for analyzing the team performance, as well as giving this data back to them for them to optimize their algorithms. And we have a third deployment that's planned for 𝐂icar 2025, wherein the registration deadline that we have set currently is April 15th. So it's still open, and if anyone is interested in this room, they can basically find more details by scanning the QR code or the link that's given on the slide. So I think with that we can move on with the demo, which will basically demonstrate this exact case study that I highlighted multiple times now, and demonstrate how it can be effectively validated systematically based on the different test parameters, which are the times of the day and weather conditions, as well as the different algorithmic variants, which as I talked about, are the different perception models, planning models, and the control models. So this is the system architecture of the model-based systems engineering framework. What we have here is the perception module, the perception component in the architecture that's tied in with the requirement of how many detections, or is there any consistency in terms of the detections or not. Then we have the planning module, wherein again we have a requirement based on the smoothness of the generated motion plan, and then control module, which controls the vehicle motion as well as the lights in terms of the vehicle lighting control for engaging or not the vehicle lights during different times of the day or weather conditions. And then a final component, which is the simulation component itself, which co-simulates with MATLAB Simulink to generate all of the data from the simulator to all of these different modules, and collecting the data from all of these different modules back to the simulator in real time. And again, as I highlighted, there are different algorithmic variants, for example the control system, and then you can basically define all of the different configurations for different variants. So you could have a simple controller such as model free controllers or parametric controllers, or you could have model based controllers or even learning based controllers. So one thing that we could probably highlight is the perception component, wherein we have different machine learning models, specifically the YOLO models as I highlighted, defined as different variants, and the algorithm will basically sweep across all of these models to validate them across the different times of the day and the different weather conditions. So here is the test harness, wherein we can define the different parameters such as the times of the day and the weather conditions, and then we can also define cleanup routines and initialization routines to make sure that all of the simulation instances are launched and terminated successfully without leaving any overhead that might basically create inconsistent results while running the tests one after the other. And then finally we have a scripted iteration wherein we are defining the different variants of the algorithms themselves. So here we have just reduced them to not include all. So we are considering the variant configuration 1, 2, 5, 6, 13, 14, 17, and 18, for example, which basically resembles to a configuration wherein we have a specific perception module, a specific planning module, and a specific control module. And then once that is defined, what we can do is set up a final custom criteria wherein we can define what are the different data streams that we want to save, or is there any customization that we want to do to them before saving them. Are we saving the raw data, are we processing and then saving the data, and all of that, wherein we can also verify the requirements. So we have, as I mentioned, we have set requirements for every component and the system level requirement of not colliding with the animal herd. But here is where we actually check if or validate if those requirements are being satisfied or not for every test that we run. And then with a single click of a button, we can basically generate all of these test scenarios. So it's basically analyzing what are the different iterations that it needs to perform, and then it will launch the simulation instance, conduct the test, and terminate the simulation instance. So right now, since this is deployed on a 3-year-old laptop, we are doing this sequentially, but of course there is a possibility of parallelizing this on a better compute configuration, or especially in cloud with high performance compute resources. So it's still compiling all of the information, and once that's done, it will spin up the simulation instance, execute the test, and then terminate it successfully.
So maybe while that's running, does anyone have any questions, especially anyone who has to either drop out or head out and come back?
So I'm from the software engineering community. So one thing when we look at this kind of simulator, one thing that's very interesting to us is the capability or flexibility of the simulator to construct different kinds of driving scenes or traffic scenarios. For example, I'm interested in generating a rare driving scene where I have a highway, but the exit is on the left-hand side. I was wondering how flexible it is, or whether it's capable to simulate this kind of driving scene in your simulator.
Yes, of course, it's possible, and it's pretty easy, I would say. So we have something that we call Autodrive Infrastructure Development Kit, IDK, and what it allows is it offers a range of modules of environments, and with anything like and of course it supports open scenario and those standards as well. But even if you want to define them manually, you could just basically arrange the environment in such a way to create such a scenario, and then, as I mentioned already, to the different vehicles, any of them could be basically tested under such a scenario.
So jumping on that a bit, since we're from the same community and we focus on software testing a lot. So the kinds of things that our community does often is, for example, taking for instance, I think you call them your KPIs, or maybe your test metrics or matrices, and then designing algorithms that would generate scenarios to maximize the possibility of getting all of those to fail as much as possible,
right.
Automating that. And then beyond that, if they fail, can we even automatically fix them? So things like that. And as I was saying earlier, like our community has become like addicted to bugs one way or the other. Maybe that's a good thing. So I'm wondering, in terms, especially since like we're hoping through the AutoWare COEs, for example, to be able to have like CADRI support testing of AutoWare or AutoDrive on AutoWare or Blue Ice on AutoWare, and then find bugs in AutoWare and make AutoWare easier to use, more reusable. From your perspective, are there any particular kinds of maybe features, capabilities, functionalities you would want from something like CADRI? like that would help support, for instance, your research. I mean, same thing for Blue Eyes, same thing for anything anyone else is working on here.
So from what I saw in the demo, it looked pretty much like from perspective of the infrastructure, it looked pretty much adaptive to what we could apply directly with AutoDrive. So for example, with the simulator itself, you could just switch the container for the simulation instead of Carla or SVL. You could now add a variant for AutoDrive container, and what that can do is basically we have a system to deterministically time step the physics models. So even if you're running on low compute, it can guarantee that your time stepping is deterministic, and that basically helps synchronize the data transfer between your autonomous driving software and the simulator, and only then time step in the simulation. You can also paste the simulation time stepping to real time to make sure that any delays in your latencies in your autonomous driving software stack would actually affect the real-time performance of the system. Because if your autonomous driving software is running slower than real time, but your vehicle, of course, in the real world would be running in real time, that latency could actually induce a failure case, and that's also something that you can capture. Another thing is with the digital twinning framework, now you can also introduce selective or complete digital twinning, in that you can synchronize the simulations with real world data that can be updated as fast as 60 Hertz or 100 Hertz even, or on demand at a slower rate, or even at the time stepping of different days. For example, if you have a static environment, you don't need to literally update it at every second because it won't change much. Something like a weather, you can keep checking hourly or every minute rather than having to do it every second, because there won't be any variation at each second. You could do that if you have the compute, but you can choose not to. But for some things like the vehicle or the traffic simulations, you can actually use much higher frequencies to update or synchronize the real and simulation environments, and that could basically add to the validation suite as well. So I hope that answers your question.
Yeah, I think so. And if we need any clarity, we'll definitely reach out. But this is, I mean, from my perspective, very exciting and definitely a very interesting software engineering challenge to validate and verify all of this.
So probably just to highlight, all of these simulations are forced to run in real time, meaning the simulation pacing is adjusted to run all of these simulations in real time, even though they have the capability of running faster in real time.
So given this pipeline, like we want to inject faults, we want to inject bugs, or we want to even do like some code injection, like let's say along the pipeline. Is this the code is mostly based in MATLAB, or you're just doing the orchestration from MATLAB, but the code is in?
So in the demo that you see, everything is implemented as a Simulink model. Okay. But as we have highlighted, we have open APIs for Python, C, C++, as well as frameworks like ROS, ROS2, or AutoWeb. So it doesn't matter which mode or which framework is interfaced with the simulator, it would still work.
Yeah, so like say, like going back to Josh's question, like we want to now basically have hooks into, like it would be hooks into Simulink models, right?
For this demo, yes.
Yeah, and but in the auto drive case, that would be hooks into like the ROS.
Yes. In general, it could be hooks into ROS, ROS2, or AutoWeb stack, or even like if you have standalone.
What would be like an interface to sort of either to manipulate parameters or to inject some code?
So it could be done parametrically from within the framework itself. But with something like System Composer that we are trying to demonstrate over here, it could be done via a third-party software like MathWorks System Composer, wherein you can orchestrate everything and then utilize the framework.
Yeah, so then let's say we want to now, we inject some code into, let's say the localization,
Right.
or video link planner, and we want to see the effect of that under this domain randomization. But each instance will have to then be executed basically as a black box, right? You have to let it run, then see the terminal state, and then determine whether it's crash, no crash, or whatever criteria there is, DTC or
Yes.
that we are looking at, right? But you don't need to run the UI aspect. Right? You don't have to run the graphical aspect.
No, it's
It can
not
be
necessary.
headless.
Yeah, it could be headless, yes.
And how heavy is that? Just to
So it depends on the scenario exactly. So for something like a full-scale vehicle wherein we are having complicated vehicle dynamics and vehicle environment interactions, even if you look at the fidelity of the environment, it would typically be recommended to run such scenarios in headless modes because they would be pretty intensive. But for simple scenarios, we have observed even with the GUI rendering upwards of 60, 100 or even 240 Hz of frame rate. So it's pretty real time for a single scenario. Of course, depending on the compute availability will change. But running headlessly would, I would say, if not more, at least 5 times boost. And that again depends on whether your bottleneck is in terms of the CPU computations,
Right.
that is mostly vehicle dynamics or sensor simulations, or is it more on the GPU side, which is the rendering or say LiDAR raycasting or things like that. So that is also something that affects the performance.
I have a really quick question about the sensors data simulation. So when we were testing our physical vehicle with AutoWear, we found that AutoWear was extremely susceptible to rain. So even if it's just dribbles outside, AutoWear will treat individual rain droplets as obstacles, and the planning module will make it stop dead in the middle of the tracks. So does the AutoDrive simulator have the ability to simulate the effects of rain or fog on LiDAR? Okay.
But that again comes with a twist or a caveat of performance hit, where if you're trying to imbibe physics within each of the raindrops,
Yeah.
it will significantly affect your performance because that kind of moves you from rigid body dynamic simulation or multi-body dynamic simulation to finite element analysis kind of method. It's not exactly FEA, but you're trying to at least have a lot of particles that are you're simulating physics based rather than just rendering them. And yes, to answer your question, yes, it is possible. You can affect the raycast hits or even the collision of the drops, and that can impact your tire surface properties, for example. But if you do that, your simulations won't be real time anymore,
Yes. Okay. Thank you.
or may not be real time anymore, depending on how many rain particles you're simulating.
Yeah, and a follow-up question to that. So you showed that you use camera and LiDAR to reconstruct a part of the field. So how long did that take?
So it depends on the data that you have. So we experimented with a lot of collecting a lot of data and then seeing if more data is beneficial or less data. But it usually takes, I would say, a few hours, 3 hours, for it to completely reconstruct a scene as big as our campus, which is like a few acres, I would say, not very big. But as the environment scales, that's something that will take time. Yeah.
Okay, and it was run. It was the reconstruction is ran on the HPC or
No, this was on the lab.
Oh, okay. Okay. Thank you.
But even like it needs to be played around a lot in terms of the different parameters for it to make it work as good as you see in the picture here. And it again depends on the size, scale and lighting conditions, of course, because sometimes it just doesn't capture that accurately. So it's a lot data dependent, I would say, than the time that's actually required.
And the reconstruction is able to reconstruct the trees as well, or
Yes.
oh, okay, wow. So what we did was if we detected a tree, we would just say at this XY location here is a tree, and then we have a follow-up code that puts the trees in instead of reconstructing the trees.
Okay.
Because and correct me if I'm wrong. So if I put a segmentation camera in AutoDrive, would it segment everything, or would it just treat everything as background?
It can segment,
Okay.
depending on whether you are slicing your environment on the different layers of graphics rendering.
Yeah.
But if you're not, then of course it will treat everything as
Oh,
background.
I see. Yes. Yeah. Okay.
So for the razor case, you'll have like a multi-body model? Or?
Yes.
Okay.
And you can also have detailed terra mechanics models for it. we didn't demonstrate it in this conference, this presentation. But yeah, you can also have detailed tire and terrain properties. You can even deform the terrain and tires based on the tire pressure or the soil properties. And of course, that will add to the computational overhead. But if that's something that you really want, then you can simulate those conditions as well.
But these are like what tire models and
You can have different tire models. You can have Pajeka models. You can have for this terrain, you can have basic
Force
truss
norm-
basis or force kind of
normal
models.
force-based deformation, or you can have Baker-Wong models or other models as well.
because the friction that you get in any simulation is just the friction of the game engine, right? It's game engine friction. It's not
So what we have actually implemented in AutoDrive is custom scripts that define the physics. It also applies to the vehicles as well as the environments. Where, for example, in the small scale vehicles, we are basically just as simple as they are. We are not taking care of any other complicated powertrain models, but for full scale vehicles, we are. So those are the things that can be modified, and we have all of those templates available as well. So even for generating different environments, you can have real world height map data, and that can be reconstructed within a few seconds. You can have friction maps from real world, and those could be overlaid onto your environment to actually sample the tire terrain interaction and implement those friction models. So yeah, that's possible.
I remember you have one slide showing that using generative AI to create NPC or pedestrian testing. You provide prompts, right? I'm curious, what's the yes, this one. So what's the interface? I mean, do you provide a interface for the generative AI, or do you provide some standard format like open scenario for that to kind of operate with?
That's a very good question. So right now this work is still a work in progress, I would say. So the way it's currently implemented is we have a rule-based multi-agent system. The high-level agent is still a generative model, an LLM to be specific, and we have tried with different LLM models. And then what it does is basically describes the scenario, which is passed by different rule-based agents. Every agent, for example, there is one agent that takes care of pedestrians, there is one agent that takes care of other vehicle models, there is one that takes care of the environment lighting conditions, another for the weather conditions, things like that. So what we have is, instead of just giving the LLM a direct interface to modifying the simulation, which could basically create something that's not physically possible or that's very weird in some sense, we have these rule-based agents that basically dilate that information to construct scenarios that are physically possible.
Provide some options.
Yes.
Gotcha.
But yes, as you said, there is a way to integrate that with something like open scenario, wherein this LLM agent could modify the description in a specific way. We could have RAGs or something like that implemented so that it's consistent, and then that would be basically passed on to the simulator to launch or simulate that scenario. But we haven't yet implemented or tested that. But that's mostly possible if I'm not wrong. What you see here is for scene modification online, not generating the entire scene from scratch. So just wanted to highlight that difference, where the scene is already the same. We are just trying to modify the scenario, wherein you can add different live element or dynamic changes to the scene.
Question about this scenario specific as well. So for this pedestrian to appear at a specific time, do you have to specify in the scenario, or can you like dynamically weld scenarios in simulation?
Yes, you can dynamically specify that.
Okay.
So if you see the prompt, it says across the Evo vehicle's path. So the path of the vehicle that it's taking, the model has to analyze it. And again, the first part of the trajectory analysis is done by a rule-based agent. That basically creates a feed-forward motion plan for the vehicle, which is now passed on to the LLM agent. And then the LLM agent can decide or the time the spawning of the pedestrian based on the plan that has been generated to make sure that it actually cuts in front of the ego agent.
So that means the pedestrian is generated before the scenario is simulated?
No, so if I were to show the actual GUI in this case. this is actually done live. So we have a user interface which basically allows you to change different parameters online. The interface was hidden in the videos earlier because we didn't want it to cover the different elements that are happening in the scene. So if you see any of these videos, we are requesting live changes. So this is when the simulation is actually running. Here is just a simple test of making sure that the framework is working and benchmarking the different LLM models. But you can get the idea that we are doing, we are prompting it as the simulation is taking place and it's updating the parameters live online.
Yeah, not understand. So you're sending prompts while the simulated stuff is added. The follow-up question. So if you add a pedestrian, so let's say if you add a vehicle, the vehicle prompt being the vehicle also follows the hit. So does that mean the obstacle will dynamically analyze the AV's position and try to follow, or will it be a predefined speed that just follows the vehicle?
So it all depends on the architecture that you have. For example, you could define a rule-based agent that ensures that it follows the vehicle, or it could be just a simple heuristic with a constant velocity.
Well, how realistic is the physics for the obstacles? Well, I'm asking that because, for instance, for SVL, what I saw was we set waypoints for the obstacles. Let's say the speed is 10 for the first waypoint, 20 for the second waypoint. The vehicle also doesn't accelerate. It changes speed when it reaches the second waypoint.
Okay.
So I think that is some simulator struggle handling the obstacle dynamics. So how well are the obstacle dynamics handled?
So we again have a bunch of options. So it could be as realistic as the ego vehicle itself, but then it would of course hit on the performance because you would have all the complicated vehicle dynamics models implemented for all the different vehicles in the scene depending on their properties. Or it could be a simple heuristic, like a very basic vehicle dynamics model or a constant velocity model, or basically anything, because everything is scriptable using object-oriented programming. So you could just create an instance of the existing objects or existing class of the vehicle and then just modify its behavior based on the requirement. So what you see in this video is basically we have asked it to add a mid-scale Ackermann steered robot doing a skid pad maneuver. What it does is basically looks up for the different classes of robots that it has in its library, picks up mid-scale robots first, then goes to the Ackermann steered, which is something like the Hunter AC that you have, and it also picks up the maneuver. It goes to a rule-based agent, asks whether it has a defined maneuver for skid pad. If it has, then it picks up those control commands and then relays them to the non-ego agent. And then that's what you're seeing here. It first spawns up the vehicle and then that vehicle starts doing a skid pad maneuver. Here we are actually considering the vehicle dynamics and collision interactions. And that's why the OpenCAV, when it came across it, it actually used the LiDAR data to pick up that it's a moving obstacle and then make sure that it brakes, lets the robot pass by and then continue its course.
So I'm wondering how many scenarios are generated by these tools, and if this presented scenario generated, so if this presented scenario that meet your requirements are selected from a group of generated scenarios, or your tools can exactly generate a scenario that meets your needs.
What was the last part?
So if this presented scenario are selected by a human from a group of generated scenarios, or does your tool can generate exactly the scenario that you want?
So with the LLM-based orchestration, it can generate pretty much anything that it wants, but you can also, of course, define manually the constraints that you want. So example, for the rule-based agents that are not generative agents, you can have constraints that are imposed on the generative model that wants to just generate anything. So for example, a simple constraint here was a model library that we had fed to the rule-based agent based on the available models in the Autodrive simulator, and only one of them meets the criteria of being mid-scale and Ackermann steered, which is the Hunter AC that you see here. But again, it will vary based on the requirements, so it's not hard and fast, but more flexible, I would say. The idea here is not to generate a specific scenario that you can do with any of the currently available scenario description languages. What the idea here is to imbibe more naturalistic scenario generation, where LLMs, for example, can be really creative, and that's what I tried to show in one of the, this one. So here I'm only asking it to generate a pedestrian cutting across, but it would automatically, by the context of pedestrian, since the LLM agent knows that or thinks that there can be a pedestrian sign and queries a rule-based agent, if there is one, please add it. That's what you see here, that the pedestrian sign has been added without explicitly asking. So these kinds of creativeness of the LLM agents can be harnessed to generate scenarios that are out of imagination or at least out of the standard parametric sweeps that you could have.
So if it's possible that the generated scenarios, so like in this scenario, the vehicle has already driving way, but the pedestrian is not on the trajectory of the vehicle.
Yes, it could be possible, but the way we have constrained it, as we highlighted, is by adding the rule-based agent which has the information of what the vehicle trajectory is and, for example, where the vehicle is currently traveling. So it's technically privileged in a sense, but in simulation you can enjoy the benefits of that.
I think you mentioned a couple of times this centurial gap. I'm just curious in general, not specifically about any slides, but in general, what are the key challenges that you experience of the centurial gap, and what are the solutions that you come up with?
So, as I highlighted, there are two, like the perception interface and the control interface are the two where we encounter the centurial gap. One is if the data that's coming in or coming into the perception module of the same fidelity or quality as it would expect in the real world, and the other end of the spectrum is the control, wherein is your vehicle behaving in a similar way in the simulation as it would in the real world. So right now we have experimented, I would say, more on the control aspect of it, and we are working on the simulation aspect. But in the control, what we saw was, for example, the vehicle behavior or the vehicle dynamics models or the vehicle environment interaction matters a lot, how you define it in the simulation. Of course, it also hits on the real-time performance capabilities, but with added information of or exact replication of the vehicle or the environment that you are working with, it certainly adds a lot to the quality of the data that you are working with respect to the. So for the ICAR paper that I mentioned, what we observed was creating the environment digital twin and the vehicle digital twin, and then using the data from that, the data generated from that to train the model, benefited a lot as opposed to data generated, even more quantity of data that was generated from a generic environment. There is typically three strategies that we employ for bridging the centurial gap. One is system identification, where you try to first bridge the real to sim gap in order to create higher fidelity simulations, such as what you see here. For example, this scenario could give you really photorealistic data or literally photorealistic data because this data was captured from the vehicle's camera itself. And also because we use the same LiDAR that's on the vehicle, the LiDAR data would be also consistent. So that kind of bridges the perception interface. In the side of controls, we can have the vehicle dynamics models validated across real world data. So you give same control inputs to a real world vehicle, gather the data. You give the same control inputs to the virtual vehicle, gather that data, and try to minimize the difference by imbibing an optimization loop to tune the simulation parameters. So that's system identification. Then you have augmentation techniques where you can have simplistic simulations, but then you can add robustness to your algorithms themselves. So we have experimented with robust control or robust optimal control strategies to now have zero-shot transfer even with kinematic models, and have extreme disturbances in the real world in terms of the friction coefficients or adding disturbances manually, and it still works pretty well. Or you can have similar kind of robustness metrics or pipelines infused within the perception stack. For example, you could use generative models, you could use style transfer models to actually have simple scenarios being replicated or kind of retrofitted as photorealistic scenarios from the real world data live as you're deploying the algorithm, and that could basically bridge the gap. And the third part is adaptation, where typically you would need to retune your algorithms when you're deploying in the field. That's considered a one-shot transfer, not a zero-shot transfer. So, but yeah, that's still a centurial.
System ID adaptation, what's the second one?
Augmentation. So, system ID is one step or zero step, depending on whether you're doing online system identification or offline. Adaptation is one step, definitely, because you need to adapt while going from simulation to reality. And then augmentation is a zero shot, typically, where you kind of augment on the fly, either in the training phase or while deploying your algorithm.
Thank you.
possible from user experience perspective. In the demo that we're showing, there was a compilation time that took some time.
Yes.
What exactly is being compiled?
Sorry?
So what exactly is being compiled?
So the entire autonomy algorithm that we have devised in Simulink, so all of the implemented models in here, they are being computed. It's not the simulation that's being compiled, it's the autonomy algorithm, and first it basically generates the test matrix. That doesn't take more than a few seconds. But if the scene is not compiled, so again, just to highlight the difference, we are not running in interpreted mode. We are actually compiling the code for hardware generation as well.
For
Hardware deployment. So we are using code generation to make sure that we have C++ binaries to ensure that we could actually transfer this algorithm from simulation to reality. So this is basically a model-based engineering framework where we are defining the properties of the system as models, but they can support code generation to actually deploy them on the real hardware as well, on the target hardware as well. So that's what the compilation is.
So if I'm testing the C for AutoWare plus AutoDrive, and I have AutoWare compiled already, AutoDrive compiled already, if there's still a compilation time?
No. So yeah, if I put one of the slides, this would be a video, but what you see here is basically the different interfaces with AutoWare, and this is from the launching the scripts or the packages to interfacing them in real time. You don't have any compilation time here. Both the simulator and the AutoWare stack have already been compiled.
In this demo, are you using the QR code around the test track and on the robot for localization? Is there a RTK sensor on there, or just pure localization data from AutoWare?
So this is UCI-based localizations. We are using the LiDAR to localize it within the app.
Okay, so you're not using the QR code on?
No,
okay.
not for this demo or example.
And is this AutoWare Universe or AutoWare AI?
Universe.
But I see that on the two screens here, it looks like you're running it on a ARM-based machine there, right?
Yes, this is a Jetson.
So you were
Jetson
able to...
Orient Nano.
What was that?
Jetson Orient Nano.
So you were able to run AutoWare Universe on a Jetson Orient Nano?
Yes. Not all of the packages I would say, but it's sufficed for the
Okay.
on scale reality.
Okay.
For this vehicle as well as for the effort.
Okay. Thank you.
Of course, it takes a lot of time to compile, but we also overflew the RAM a couple of times.
Because one question is the transfer of the code, right, to the platform. So what kind of mechanism? Is there a mechanism, or is it kind of separate?
There is no mechanism. The mechanism is the framework itself, where it allows you to interface any kind of API. Through the API, it allows you to interface any kind of framework. What it essentially allows you is basically use the same algorithm or the framework that you are developing your autonomous driving software, interface it with the simulation, and then directly copy paste all of those on your target hardware. For example, things like AutoWare, you can just literally copy paste the packages onto your physical test bed, compile them and run them. Because the framework is still the same, just the API is different. And if you're running in the digital twinning mode, you don't even have to do that. You can choose to just sync the real and simulation instances to update the parameters accordingly. And you can even have the code running on a third machine. So simulator running on one machine, code running on another machine, and the physical test bed just connecting to both to just synchronize the data.
Okay. So it's 2:15. We're actually I guess the plan was originally start session 3 at 2, but then it's a workshop. We can be flexible. You might need a break. Maybe other people might need a break before we move on to other stuff. Warul and Ziran aim to talk and discuss next. how about we take a break, at least for 15, maybe 30 minutes, and then we jump into yeah, whatever you want to talk or discuss with respect to all this.
Great job, guys.
Yeah.
Lot of work.
Yeah.